Hey everybody, Mr. Burrell here. We're going to talk about homework assignment. What are you even talking about? Homework assignment 13.4, which is rotational symmetry. So, question 1, what does it mean for a shape to have rotational symmetry? Well, last video we talked about reflectional symmetry. And reflectional symmetry was where you could reflect one shape over a line and the shape would land on itself. Here, we want to talk about, well, if a shape can be rotated and land on itself, it has rotational symmetry. So we kind of want to look at that idea and see kind of where we are with that. All right, so first of all, we want to fill this in. We talked about this in class, and if you don't know the answer to this level 1 question, oh, and I just told you the definition. If you don't know how to fill out this table here, I'm going to start going through some problems down here, and I hope that you can see some patterns, because like you'll see that for a triangle, the number of rotational symmetries, well, I'm going to tell you that here in this part. And then you'll do the quadrilateral on your own and the pentagon on your own, and then we'll talk about a hexagon over here. Okay, so just notice that I'm not filling out this level 1 part of the table right now, but I hope that through my examples you'll be able to see how to fill that out really easily. All right, let's take a look here. So the way that I see this is kind of like, I almost imagine a big circle surrounding this shape like this, where the corners are touching the circle and this dot is here in the middle. And the reason why I do that is because I know that if I turn this shape 360 degrees, that my dot is going to end up back on itself. In fact, that's one of our symmetries. Every single shape, you can turn any shape on the whole wide world 360 degrees and it will land on itself. It doesn't even matter what you rotate it around. You could rotate it around any point. And if you turn it 360 degrees, it's going to end up right back where it started. Okay? So that's like a given on any of these shapes. That's awesome that we have that available to us. But we want to find more. So in my brain, I kind of am imagining turning that triangle and realizing that as I turn that triangle, I could have stopped here, and that dot would have rotated to this dot would have rotated to this dot. Or I could have done it like 2 turns like this to get this dot onto this dot. Or I could have done it, the full 3 turns. So I guess what I'm trying to say here is I kind of imagine that I'm taking 360 degrees and I'm kind of like cutting it up into like 3 pieces almost. Again, like I know that this full circle here is 360 degrees, and you can kind of see that I've cut it into 3 equal parts. So it almost seems to me like if I take 365, 360, sorry, I'm thinking about days in the year, and if I divide that by 3, then that should tell me, well, 120 degrees. I think what that's telling me is that this first turn here was 120 degrees. And if I turn it 120 degrees, I'm going to get my triangle, this dot, to land on that dot. But like I said, I could have rotated it 120 degrees 2 times to end up over here. So 120 plus 120 is 240. And as I had mentioned before, if I did 120 plus 120 plus 120, well, that just gives me 360 degrees. So a triangle has 3 rotational symmetries, and I can actually write that right here. Okay? That's kind of cool. All right, let's take a look down here. So I think we've got the same idea here. Let me start with a dot. I'll start with here. And I could rotate it this much, or I could rotate it that much twice to end up here, 3 times, 4 times, 5 times, and 6 times. And I'd end up right back where I want it to be. And kind of the way I drew that, you can kind of see that circle happening on the outside. So with a hexagon, it looks like we're going to have 6 different rotational symmetries. And again, that's because I could rotate this dot here, 1, 2, 3, 4, 5, or I could do a full turn to do 360. And in fact, while we're on that subject, couldn't I have rotated it however much this is, 1, 2, 3, 4, 5, 6, 7 times, or 8, or 9, or 10, or 11, or 12, or 13, 14. There's an infinite number of rotational symmetries, but I think that's why up here it says that we want to know how many rotational symmetries are less than 360. So I guess what I mean by that is, like in this triangle example, we could have done 120, 240, 360, or 360 plus 120, which would be 480, or 500, or 620, no, 720. So you can see we can keep going around. So we're just going to limit it to numbers under 360 and just know that we could do more. Okay, why don't I do that same process that I did before then? Because it kind of seems like I'm taking 360 degrees and dividing it into 6 equal pieces. So this whole circle would be 360 degrees, and I'm dividing it into 6 equal pieces. So 360 divided by 6 is going to equal 60 degrees. I think what that's telling me is that this angle right here, or this rotation, is 60 degrees. So I could rotate this hexagon 60 degrees, or like we said, we could rotate it twice. So that'd be 60 plus 60, which is 120. Or we could rotate it 3 times, which is 180. Or we could have done it 4 times, which would be 240 degrees. Notice I'm just adding 60 degrees each time. Or 300 degrees, or 360 degrees. I know I wrote that really sloppily, but I count 6 symmetries there. 1, 2, 3, 4, 5, 6. Cool. Hopefully you're starting to see some kind of a neat pattern going on here. Let's try that one more time. Oh my gosh. Okay. So, this is 7 sides here. So I know that I could take this corner and rotate it here, or here, or to here, or to here, or here, or here, or here. So it looks to me like I'm kind of taking this polygon, this regular polygon, and breaking it up into 7 pieces. So why don't I take 360 divided by 7? Ooh, I got a crazy decimal. Oh, but good thing I set here at around 2 decimal places. Okay, so the decimal I got was 51.43 degrees. Well, I could have done that twice. So 51.43 plus 51.43 is 102.86. Or we could do 51.43 times 3 to get 154.29, and so on. You should continue this, adding 51.43, or you could do 51.43 times 1, and then times 2, and then times 3, and then times 4. Either way, you should end up with 7 symmetries, and your last one should be 360, because every single shape has a 360 degree rotational symmetry. Okay? Well, I hope that's helpful. I'm hoping that you're seeing a pattern with these kind of equations that I'm writing here. I should have written this here. As you start to look at these, is there something about the word non-gon, 9, that will help you? The fact that this is a 9-sided shape, is there some pattern that you're seeing with this 7-sided shape and what we did here? And the 6-sided shape and what we did here? And this 3-sided shape and what we did here? Are you seeing a pattern between the number of sides on these regular polygons and the number of symmetries that they have? I hope so. That would be cool if you did. Let's talk about this. So it says here in question 13 that the shapes in questions 1 through 5 were shown with their centers of rotation. So in other words, if you look up here, I actually gave you the centers of rotation. I told you what we were rotating around. But the question here is that if I didn't give you the centers, like I didn't give you them here, is there any way for you to find them exactly? Kind of just want an explanation about how you might do that. And I have some pictures here if that helps you with your explanation, and a little hint that maybe you want to, well, a hint for those of you that are here. It might be helpful for you to go back and look at the last video or the last homework assignment. If you look at the pictures in the last homework assignment, you might be able to kind of start to see a pattern with the centers of rotation and how that relates to lines of reflection. Okay, so that's my huge hint for you. I also, just to reward people who have been watching, in order to help you with this question here, I've tried to give you a lot of hints in the pictures that I've been drawing. So maybe go back and look at those pictures and use some information we know about triangles. You might want to Google the, oh my gosh, I'm going to fix this typo, not angel, but angle, the triangle angle sum theorem. Maybe you want to look up what it means to be an isosceles triangle as well. These are things you can Google pretty easily, or if you pop in a lab or just ask your phone or whatever about those two things, maybe that will help you with this level 4 question. And there's even a bonus question. For the second time this year, you can get bonus points. I will give extra credit for anybody that can figure out the answer to that question there. All right, you guys, good luck. I'll go fix that type. That's really embarrassing. Sorry, I keep pausing it. That's embarrassing. Ignore me. Moving on. Okay, bye.